It's very nice to have you here again. And I mentioned that next week we're going to have a 1-week break and then start again on September 1st. We'll have talks by Jinsum Wu, Nilanjala Datta, and Avi Vigderson. And today it's really a pleasure to have Laurent Saloff-Coste. He's an expert on probability analysis, geometry, random walks. He actually studied with an undergraduate friend of mine, Nick Varopoulos, who was professor at the University of Paris and is now at Cornell. He had spent some time at MIT, had been chair of the math department at the Cornell University, won the Rollo Davidson very prestigious prize in probability theory, and will tell us today, is any compact Lie group uniformly doubling? So Laurent, it's a pleasure to have you here.
Thank you very much, Arthur, and thank you everyone for coming to this Zoom seminar. It's the first time I give a Zoom seminar. I've given many lectures to my students, but the first time I give a Zoom seminar. So it's a pleasure to see that I have old friends that are attending, in particular my former student André Jouc from Paris. I don't know where he is right now, and also my co-author Masha from Connecticut is here. I'm going to share my screen. Please ask me questions anytime. Unmute yourself and interrupt. I'll be happy to try to answer. Also, it sometimes happens that my iPad freezes when I share it, and in such case, the solution is easy. I just have to start the sharing again. It takes a minute. So let me know if that happened, because sometimes I don't realize that that's what happened. Okay. So my talk is about joint work with Nathaniel Eldredge and Maria Gordina. It's a project that has been going on for many years. It started when Nate was a postdoc at Cornell, probably almost 10 years ago, maybe even more. And it ended up raising the following question: is it true or not that any compact Lie group is uniformly doubling? And the picture we have here is maybe the sun, or in fact, it's just a picture of two concentric balls. And it illustrates the fact that this doubling condition that I'm talking about is simply the condition that the volume of the ball of center X and radius 2r is not bigger than a constant times the volume of the ball center also at X and of radius r. So you double the volume and you want to have control on the amount of volume gain when you do that. And this control is supposed to be certainly uniform in the position of the ball, so the center X, and the scale of the ball, the radius r. Well, sometimes it's a condition that you can assume for all r smaller than 1. Other time you want a global condition that is all for all positive r, all location, and that case for us, that's what we want to think about. But in the title, the word uniformly here doesn't refer to this uniformity with respect to the center of the ball or the radius of the ball, but to something else, which I am going to explain. So this is a doubling condition. Observe that the multiplicative constant in Euclidean space is 2 to the n. I don't know why it says dimension 2 in dimension n, I meant to say. So obviously, if you are in a Euclidean space, you can use dilation to compare volume, and the constant involved is obviously 2 to the n. There is nothing mysterious about that. And the other thing is that obviously this property doesn't hold in hyperbolic space or in trees or any kind of thing that grows very fast, because doubling limits the capacity of the volume to grow. In fact, it means that the volume cannot grow faster than a certain power. And so that eliminates hyperbolic spaces of any type. Okay, so this question comes from geometric analysis, and I want to explain a little bit this background, and this is a very short and limited introduction of to geometric analysis. By the way, geometric analysis is such a large subject that it means many different things for different people. So I don't mean to define it for everybody. I just explain what it basically is for this talk and for myself. So we are going to talk about compact Riemannian manifolds. And so they have a Laplacian, which I define as a positive operator from a spectral point of view. So if you have in Rn, that means that my Laplacian is minus the sum of square of the derivatives instead of the usual and more classical sum of squares. And of course, M is Riemannian, so it's equipped with a geodesic distance function, and that defines the geometry of that object, and we'll use this a lot to define the balls. And then now this Laplacian is essentially related to this integration by part formula. So if you are on M and you integrate U against the Laplacian of V against the Riemannian measure mu, then it's the same thing as the length or the scatter product of the gradient of U and the gradient of V in the tangent space, that integrated against the measure. And by the way, this formula show you that this operator is spectrally positive. And that's the choice we made. Okay, so now what is geometric analysis? Well, it's analysis and geometry together. So it is a question of relating geometric parameters to analytically defined objects. So here are a few of them that are of interest to us today. So the diameter d, oops, that happens all the time. The diameter d of the manifold, the volume function. So you see the volume function here is very important to us. Of course, it's a volume of the ball of radius x, and of center x and radius r. And of course, so these are very simple, basic geometric objects. What is the first analytic object we can talk about associated with this Laplacian? Well, this Laplacian on the compact manifold has a discrete spectrum. And so we have a sequence of eigenvalue, which I repeat according to their multiplicity in my list. 0 is a bottom because it corresponds to constant functions. Lambda 1 is what we call the spectral gap for this, and it's least non-trivial eigenvalue of the Laplacian. And then you have higher eigenvalues accumulating towards plus infinity. Another very important object and very classical is the heat kernel. And of course, there are many ways to think about it and to define it. It's an extremely important object. Let's say a few properties and a definition of it. So it's a positive function of t and xy in M. And it solves the heat equation, or more precisely, it is the fundamental solution for the heat equation, so that the initial value is given by this Dirac mass at point x. And so if we look now at its object as a function of t and y, it is a solution of the heat equation with that initial condition. It's a smooth function. We have a nice Riemannian manifold, compact. There is no real difficulty. Of course, there are many people who are interested in constructing very precisely in detail this function. One way to do this in the case like this for a Riemann manifold is to use spectral theory to build up this function using the spectral data. And loosely speaking, the purpose of geometric analysis is to understand how these different objects relate to each other. Can we control the heat kernel using volume and distance? Can we say something about spectrum because of the volume on the manifold? So those are the questions. Now, I'm going to actually write down a few of these questions and again, this is a small list and it's somewhat arbitrary, but those are questions I've been interested in and many other people have been interested in. So, of course, I write the first one, which is the title question, is this volume function doubling? Bear with me, let's read the question and then we'll comment about what they say. Is it true that there is a relation between the first non-trivial eigenvalue and the diameter? And I wrote this relation in a particular way. Is lambda 1 of the order of 1 over the diameter squared? That's some sort of natural scale. Now, the next question, the last two questions are more sophisticated. So this one, the number 3, requires a little bit of unpacking to read what it says. So here in the middle, we are counting how many eigenvalues are less than S. So this is a very classical question. This function here is often denoted by W. I think it will be denoted by W a little later. As a function of S, it's Weil's counting function for the spectrum. So for instance, this function is of course a piecewise constant function. It starts being 1 on a certain interval from 0 to something, and then you start accumulating more eigenvalues. And so it's a function like that. And this question is whether or not this function is controlled by some strange integral of the volume function taken at the parameter square root of 1 over S and at any point X and averaged in some sense. Well, that's a strange thing to ask, really, but we'll talk about it in a minute. Maybe easier to understand as a first thing is the last question, number 4, which I spent a lot of time studying in my life, in my mathematical life. It's a question of whether we can control the heat kernel by something that look like the usual formula for the Euclidean heat kernel. So the Euclidean heat kernel is 1 over a constant over t to the d over 2 exponential to the minus distance square over 4t. And so this here, except for some constant thrown around, is asking whether the heat kernel on a Riemannian manifold looks like the usual case, the Euclidean case, what we know. Now, okay, so this box is kind of nonsense. If we ask this question for a single manifold MG, compact manifold in G, these questions are kind of trivial and not so sensical. The last two have some content. The first two have zero content whatsoever. The first one, well, actually, that's not true. Even the first one has a little bit of content. The first one, well, this is true because locally, when R is very small, which is the only question we should worry about, the volume is Euclidean, essentially. And so we should be able to take C roughly 2 to the n when R is very small. And otherwise, well, by capacity, this has to be true. So there is very little content in it. The second one is really free of content. On a given Riemannian manifold, well, we know that λ1 is strictly positive by a simple argument. And then we know that the diameter is finite. And so this is just the fact that we have two positive finite constants and they are comparable. So number two is really as written, if we consider it for a single manifold, not so interesting. Number 3 and 4, just like number 1, have some content. And in fact, number 3 has a very famous content because if S goes to infinity, this is, at least it's related to the famous Weier's asymptotic for the counting function of eigenvalue. Because if you look at this formula here, so if we look at this, so we expect this thing, according to Weier's formula, to behave like S d over 2. So d is the dimension here. Well, maybe I should use n for the dimension. Sorry about that. That's what we expect. And well, that's indeed given by this formula here, or the lower bound, because the volume, of course, when S is very large, then 1 over S is very small, and the volume is Euclidean, so this volume is roughly 1 over S to the n over 2. So you see that this is essentially saying that some rough version of the famous Weier's asymptotic behavior is correct on any manifold. And essentially, the content of the last number 4 is exactly the same. That is, the heat kernel at very small t behave in the usual way on any compact manifold. So in that case, in those cases, these statements are very rough versions of much better asymptotics statement, and that's the only content is asymptotic. There is no, otherwise they are kind of trivial. Okay, any question about that? Okay, so
what is the measure mu?
The measure mu is a Riemannian measure here for the compact manifold. So the Riemannian measure. Now, how to make this question more meaningful? Well, you have to ask whether they are true, not for a single manifold, but for some families of manifolds. And then they take a much more interesting life of their own, and they become more sensical. So let's look at example of what I mean by that. And I'm going to talk about 3 very basic examples to which I hope everybody can relate. So here are 3 theorems. And So the first one is about a bounded convex set in Rn. So in a bounded convex set in Rn, then it is true uniformly over every shape possible for a convex set in Rn that these four questions are have a positive answer. And so uniformly means that for convex set in Rn, the constant C doesn't depend on the convex set, it just depends on M. It means that this inequality now makes perfect good sense. For any shape of a convex set in Rn, the lowest non-trivial eigenvalue of the Laplacian, here we have Neumann boundary condition on this convex set, is comparable to 1 over the diameter of that convex set. So here, the diameter in lambda 1 is roughly 1 over d squared. And this is true for any convex set in R. So, and same thing is true for the other inequality. And now they are really pack a lot of content. So, you know, if you have a convex set in Rn and n is pretty large, many different things can happen. You know, it can be very round, it can be very elongated, etc. And so the spectrum behavior will depend on this shape very much. But number 3 tells you that the counting of eigenvalue is entirely controlled by a simple question about the volume function at a certain scale. So if we go back to this picture here, and we think of it as really not necessarily 2-dimensional, but now I went, you know, 3-dimensional or more, this volume is kind of a complicated thing to write down, but it's also a very simple thing to imagine what it is. And again, this statement in this theorem tells you that the spectral property of this convex set is, in some rough sense, completely controlled by this volume function. The last property is also very meaningful now. It says that at any location scale, the heat kernel on any of these convex sets is controlled by just the geometry, the distance function, which is still the Euclidean distance in this case, because we have a convex set, so the distance function has not changed, and the volume, which we can compute. So that's theorem 1. So this is a folklore result. Actually, I have a picture later about why this is doubling, and we'll talk about it. So the next case is very close to the question we want to talk about today, because it's a case of flat tori. So in Rn, if you have, so this is a group now, that's why it's related to the main subject of the talk. And again, well, I think a lot of people don't realize how complicated flat tori are. You know, they have a lot of different metrics, all flat, which all correspond to something relatively trivial, which is a constant coefficient metric on Rn. But when you go to the tori, there is interaction between the choice of that metric and the lattice that define your tori. And so these metrics, which are all isometric in Rn, become quite different in the tori. Again, we'll have a picture a little later. But so for this flat tori, it's still true that we have all these properties. Now, just like for convex set, it's actually a complicated matter to write down the volume function of a flat tori. But it's going to be, how does it look, the volume function of a flat tori? It looks like a piecewise polynomial function, essentially, not exactly, but up to constant. It's continuous, of course. It's a piecewise polynomial function with a power which might jump down as the radius grow. Why is that? Well, because just like in the convex set case, sometimes there are directions where you reach the maximum amount of space given to you in that direction. You know, that's because we have a compact manifold. So on the torus, you know, if your torus is very skinny like that, then at first, of course, the volume looks two-dimensional, but very quickly it looks like one dimension. And now if you have 18 dimension, then you will go from 18 dimensional to maybe one dimensional. And this might happen in many different ways, depending on exactly the shape of the tori. So this complicated volume function will control the spectrum of your tori, of your torus. And this will happen uniformly over all tori in a fixed dimension. That's the point. Okay, and the last theorem is maybe the most significant, really a central result in geometric analysis. It's based on the work of Stiao, who told us that the Ricci curvature was controlling many things in terms of geometric analysis. So on a compact Riemannian manifold with non-negative Ricci curvature, again, that's a huge collection of different manifolds, and uniformly in that collection, all these properties are true. And that's more complicated. For instance, the first question, is it true that the volume is doubling? Well, the fact that it is true uniformly for all manifolds with non-negative Ricci curvature is a famous basic result of called Bishop and Gromov. It's named after Bishop and Gromov. And in the form of the doubling, it's really actually in a paper of Shiger, Gromov, and Taylor. Okay. So I wanted to explain by a picture why it is true on convex sets in Rn that the volume is doubling, because we are most interested in that property. So here we have a convex set. And essentially, if you fix a point in your convex set and draw concentric circles, it will quickly become very clear to you that the proportion of the circle that is included in the convex set is a decreasing function of the radius. That's by simple convexity. So here in this simple picture, if you look first at the blue circle, which is the one with the smallest radius, so we found the intersection point here of the boundary, and so you can see the fraction of the circle that which is in the set. And now when you enlarge the radius, you can see that you have these 2 points which do the same thing for the new red circle. But the straight line from this point to the center will cut the blue circle. and it will cut inside. So from that, you can see immediately that the proportion of the circle that's inside the yellow region is a decreasing function of the radius. And that's essentially tell you that you have the doubling property. Okay, any question? Okay, so now we are ready to consider the main question of I want to talk about. And it's to ask a similar question in the context of compact Lie groups. So we don't need to know that there is a classification of compact Lie groups, but I always like to remind us that that's the case. So we know exactly what compact Lie groups are. Well, they have finite centers, and you can take quotient by a subgroup of the finite centers that will give you a lot of little variations. But if you ignore that by taking a sort of cover of your compact Lie group, they all have this particular form, which is they are all a direct product of a torus, that's the last letter T in this formula, and then a bunch of groups that are coming from a precise infinite list of groups, which are the classical simple groups. So you have the SU series or A series, the double SO series, depending on whether the dimension of the Euclidean space is even or odd, because they are a little bit different. The symplectic groups, and then the wonderful, strange 4 exceptional group G2, F4, E6, E7, E8. And so those are the compact Lie groups, that's all. If you have a compact Lie group, that's essentially up to a finite cover, just a product of those. Now, what is a conjecture? I want to talk about. So there is several ways to say it. The one fancy way to say it is that conjecture, if you fix a compact Lie group K, so fix a K, then the answer to these 4 questions is that it is true, it works uniformly over all left-invariant Riemannian metric on that particular K. So this is, in terms of our theorems, it looks more like this theorem number 2. We have the torus topologically, or the manifold, it's fixed. We have one tori in dimension n. And then we look at all flat metric on that tori. That's what this theorem is about. And now we do this with an arbitrary compact Lie group. So very important, here we have the set of all Riemannian metrics which are left invariant. So let's talk about what it is a little bit, this set of Riemannian metrics. We have our Lie group K. It has an identity element. And right there in the tangent space to that Lie group, to that manifold at K, we pick a metric in that Euclidean space. So we pick a metric. And we move around this chosen metric by using translation in the group. So we have a group, so if we change, we have translation that take us this, the picture identity to any other arbitrary point in the group, and that allow us to define an entire Riemannian metric on the compact group just by picking one as the identity. And we use left translation here. We could use right translation. It doesn't change anything, but pick one and we pick left. And then that's the class of metric that we are considering on this table. Now, of course, these metrics are very special, but it's also a pretty big class, and we'll talk about that later. And so the conjecture is that in that class, you can get the usual result that I described earlier uniformly over all the metric in that class. So the Lie group is fixed, the metric is left invariant but arbitrary, and that's what we want to understand. So for instance, if this is true, then, you see here I'm using the letter W to denote this function. It's because it's a Vive counting function. I have decorated everything inside with a little g. This little g is for the metric. So g is an element in L of k. And what is a measure that appear here? Well, on a compact Lie group, if you take a Riemannian metric which is left invariant, then the Riemannian measure is a multiple of Haar measure. So this measure, they're all the same, except for a multiple, a constant multiple that depend on the metric in a sort of obvious way. So mu is actually essentially the same measure for any of these metric. And the only thing that's left is the geometries that change depending on your choice of the metric. Now there is a proposition that explains the title of this talk, which is that this conjecture, which looks like talking about the spectral geometry and the heat kernel and many other things that I didn't mention, well, it all boils down just to one simple question. It boils down to the question of whether these metric are uniformly doubling. So this is not a conjecture. This is a proposition about the conjecture. It tells you that it's enough to prove that you have uniform doubling in this group for all these metrics in order to settle this conjecture. And so we should concentrate on this very basic, simple question. Is it true that on any compact Lie group, the left Riemannian metrics are all uniformly doubling? So that's the question, and that's another form of the conjecture. That's our main conjecture. Okay. So what about tori? So here I have a picture to help you realize that, what toris are, right? If you look at picture on the internet or anything, you never see a flat torus, right? There is no picture of a flat torus. It's hard to draw. You know, when you see something like that, it's a torus embedded in R3. It's not a flat torus. Think about it. The metric of this torus embedded in R3 like that is not a flat torus. The only way to draw a flat torus is to use this kind of picture where the sides have to be, of course, identified. And so this picture helps you to see that in this flat torus, you know, if you look at little ball like that, they will be exactly two-dimensional. We know exactly the volume of this little ball. But if now I double the volume, the radius of this ball, well, it will be more complicated because then I have to pay attention to what happened and there will be overlaps of this ball as drawn in R2 here, and as drawn in the torus. So the doubling property, even for tori, is not completely obvious. If you try to study it on the tori, it will be hard. You are not going to find it very amusing to do, I can assure you. But there is a very easy solution. Well, there is actually multiple solutions to that problem. So why is the volume doubling of on a torus? So in a fixed dimension, why is it true that the volume is doubling on a torus? So here are two ways to see that. The first way is to say, well, these torus are flat. So they have non-negative Ricci curvature. So you can use Bishop-Gromov theorem to tell you that they are doubling. Or you can, well, this is kind of a sophisticated proof. So the better proof is to say, well, what if we lift to Rn? As soon as you lift the flat metric of a torus to Rn, all these metric become isometric. All these metric are isometric. There is an isometry from Rn. There is only one Euclidean space up to isometry in one fixed dimension. And so the lifted object, obviously, they all have the same doubling constant, which is exactly 2 to the n. And so then there is a lemma, which actually was discovered first by Yves Guivarch, that if you take the quotient of a group by a subgroup, then the volume property is preserved by this operation. So you can prove that tori have the doubling property by proving the doubling property on Rn, which is trivial, and then using this lemma that it preserves under quotient. Okay, so I talk a little bit about curvature. You know, that's the way people have been proving doubling on geometric object for the past 25 or maybe 40 years is using curvature. And so what's interesting about this conjecture is that there is no way to prove this conjecture using curvature. Certainly not Ricci curvature, because among left-invariant metric on Lie groups, we know for a fact that Ricci curvature does all kinds of strange things, and certainly can go to minus infinity very easily, and plus infinity. So it's not interesting, and there is no way to prove such a theorem by curvature. Also, you know, now there are many sophisticated ways to try to do it using curvature, but I think my personal feeling is that they're all going to fail to prove this theorem in that generality. It will be very interesting for some special case, but it's not going to cover the general curvature. And the reason, one of the reasons is that because we are asking about a property that should be true uniformly for all Riemannian metric, without knowing it, we are talking about sub-Riemannian geometries. You know, if something is true on an object for all Riemannian metrics, then it has to be true for anything that's a limit of a family of Riemannian metrics. And sub-Riemannian metrics on Lie groups are certainly limits of Riemannian ones. And so I am talking about not only all Riemannian geometries on the Lie group, but I'm also talking in a disguise about every sub-Riemannian geometry on that Lie groups. And so that's start to look more complicated than it first looked. And in fact, I'm even talking about more than that. I'm talking about some degenerate objects that could be found embedded in my Lie groups. So for instance, in a torus, two-dimensional torus, you have real lines embedded in there and in complicated way. And so if a compact Lie group could contain strange analytic subgroups that had very fast growth of themselves, it would certainly make these properties, this conjecture, false. Because somehow you could find Riemannian metrics who, for a while, at a certain scale, would actually behave like the volume growth of an embedded subgroup inside that compact Lie group. So that's very scary. For instance, you know, your favorite compact Lie group, SO3 or something, contain free groups. Of course, free groups are not analytic subgroups, so they are not relevant to our question. But if there was a similar phenomenon in the analytic category, it would make this conjecture almost certainly false. So in some sense, this conjecture contains the fact that compact Lie group can only contain very particular class of analytic subgroup, essentially only commutative ones. Okay, so I'm going to go very fast here for this part. So there is a question, why is it true that it's enough to study the volume doubling instead of all these other analytic properties? So I think I'm going to, I had an explanation of that. I think I'm going to not go through it, but it's essentially that on the Lie group, you can prove a sort of Poincare inequalities and things like that based purely on the doubling property. So now I want to talk about the theorems. You know, so far I've talked a lot about a conjecture. I think it's an interesting conjecture, but let's talk about a theorem. And so the theorem is talking about SU2. So there is only two cases when this conjecture is known to be true. The tori, as I explained, and the free sphere, which is SU2, with its left-invariant matrix. And so this is the theorem that was proved by Nathaniel Eldredge, Maria Gordina, and myself. And so it talks about a certain class of metrics on the free sphere. And this class of metrics, in this class of metrics, the doubling property is true uniformly. And what are these metrics? Well, the free sphere is a group SU2. It can be realized as a group SU2. And so the class of metric we are talking about are the invariant metric on SU2. When I say it's the only class, only case, well, it's also true for SO3 because SO3 is a quotient of SU2, but those are the only case. So in particular, going back to our favorite statement here using the spectral counting function, if you try to count eigenvalues of a left-invariant metric on the free sphere, SU2, then it's controlled by the volume growth of that metric on SU2. And of course, in this case, the integral disappears because the volume doesn't depend on your center. We are on a group, everything is invariant, so the volume is a function only of the radius. Now, this comes about because of the existence of Milnor basis on SU2, which simplify the problem. So a Milnor basis of SU2 is three matrices in little SU2 so that their bracket circulate. E1, E2 brackets is E3, etc. And there are many examples of those. And this is a picture of SU2. And maybe it's worth, well, I can move to the next page. So the key fact is on SU2, you know, SU2 is a group of dimension 3. So in principle, you would have 6 parameters to describe a metric on this object, but there is only up to isometries, it's reduced to 3 parameters. But because you can always diagonalize a metric on SU2 on a Milnor basis. And so studying this question is just, you have 3 parameter, A1, A2, A3, which are the strengths, if you want, in each of the 3 direction given by the Milnor basis. So in this picture here, which is the Hopf fibration on the free sphere, you see a lot of circle and torus and things. It's complicated, of course. Well, this torus, this circle correspond to this direction. Now, in this picture, you have an equilateral, if you want, metric that is all direction of the same strength. Whereas we are asking what happened when you deform this and you give particular strengths, different strengths to each of the 3 directions. Okay, so I'm going to end by showing you the main theorem, so which give us not only the answer that the volume is doubling, but it gives us the formula for the doubling. And so it's interesting in itself. So here is a theorem that you want to look at and try to understand. So on SU2, if you take any left-invariant Riemannian metric, it corresponds to 3 parameter, A1, A2, A3. These 3 parameter, their value is completely free, so you can choose it. And the volume function will have this formula or behavior. Of course, for very small radius, it will be Euclidean behavior. It will behave like R to the cube. That's what we expect, of course. But once the radius has passed a certain point, and this point is exactly given by this formula as a function of the parameter, then this volume will start growing like R to the 4. And that's because at that scale, our geometry looks like the geometry of the Heisenberg group. So the key point here is that even so we are talking about Riemannian metric, the behavior of the volume is really given by a sub-Riemannian metric. It's the same behavior that you expect for the sub-Riemannian metric, standard sub-Riemannian metric on the Heisenberg group. And so this lasts for a certain interval given, described here. And after that, suddenly the growth rate of the volume become quadratic instead of power 4. And the reason for that is that suddenly you have reached maximum space in one direction. You cannot gain more volume by going in that direction because you have already made a full tour around your circle. So in that case, you are left with a sort of degenerate case where the volume become quadratic. You grow around a circle like an annulus. And of course, there is a last range, which corresponds to the fact that after a while, you are not growing at all. The volume is constant. It's a maximum volume of your compact group. But the key point here is that these estimates are given uniformly for all the range of parameter and all scales. Now you can see, depending on your point of view, this is pretty simple, or it's already pretty complicated. The volume function has 4 different stages. And on a bigger group, you will expect many more stages. So now here for you, I wrote the result for the spectral counting function. it tells you that the spectral counting functions start constant equal to 1. Well, we knew about that. This tells us that the spectral gap is given by the second parameter a square, a2 square. And then there are, again, 4 different behavior. The last one corresponding, of course, to the usual asymptotic statement, where the other one, which are true, again, uniformly over all choice of the parameter and the parameter S, giving you different stages where the behavior of the spectral accumulation is controlled by different geometric behavior on your manifold, on the sphere. So for instance, this here is a spectral behavior that is reminiscent to what happened on the Heisenberg group again. Okay, so thank you very much. I'm going to stop here. These are some reference for the pictures and for some work, recent work that are related to this question. And here at the end, if you want to read more about our work, you have the reference for our article. Thank you.
Thank you for this very nice talk, Laurent. You explained this geometry very beautifully. I'm sure that there are many questions. You can unmute yourself by holding the space bar or clicking the unmute button. Are there questions?
Yeah, Laurent, so far you only have the result for SU2?
Well, we are working on U2. Where did I do that? Coming soon.
For other groups, does it depend on getting a basis like the Pauli basis, or you call it Milnor basis for SU2?
Yeah, so on U2, we managed to use the same method and to compute the volume and to give an analog of the formula that I just showed you here. But to just explain on U2, which is just adding a circle, right? That sounds really ridiculously trivial to add a circle to something you know. But on U2, the volume will have at least 7 different zones. So the possible growth rate that you will observe will go, you know, R7, R6, R5, R4, R3, R2, maybe R. And this depends on, in U2, we are able to reduce things to 7 parameters. So there are parameters that correspond to the strengths in SU2, if you want. There are parameters that correspond to the strengths, 1 parameter that correspond to the strengths on T, but then you cannot diagonalize in the same way. And so you have to have some control of the angle of the center with the geometry on SU2, on the SU2 part. And so this gives you 7 parameters. They're all important. We know they are important because they actually tell you what the interval where this different power appears, and they really appears. And in particular, these sub-Riemannian geometries that are needed in order to understand SU2 cross T are seriously more involved than the one for SU2 alone. So for instance, for SU2 alone, you never have to worry about anything but a first bracket. And on U2, you already have to worry about bracket of length 3. So take brackets of brackets. And so it's, in a way, it's the same, but technically it's much more complicated, and actually it's very interesting in showing us what complication arise. In particular, because you are not able to reduce yourself to things that are universally orthogonal, you have to deal with a strange question of not using boxes to compute volume, but using parallelograms. So, you know, we know exactly that volume of a slanted box, like a parallelogram, is the same as that of the box. But on the other hand, you need to, you know, use this slanted parallelogram in this case and so you have to discover what they are. And that's somewhat more difficult than finding boxes, orthogonal boxes, perpendicular boxes. So we are working on that and getting, hopefully finish it soon. SU2, cross SU2 seems very interesting, but and perhaps feasible in the same way. Perhaps it's not so much more complicated than U2. But if you ask about SUN or SU24, on SU24, I assume if you were to compute the volume function, there would be about, you know, 100 different intervals with 100 different powers possible. And so I don't think you are going to be able to do it by hand. And so you will need to find a more synthetic ways to approach this question. Of course, in certain ways, it's very interesting to compute the volume exactly by giving formula like that. It's a lot of information. It's much better than doubling. It's tell you exactly what happened. So that's very interesting in itself. But on SU24, you know, this would take 3 pages to explain 100 different cut points. And so I don't think that's certainly not the way you can solve the conjecture for any fixed complexity group.
There are other questions.
Yeah, so is any of these questions relevant for pseudo-Riemannian metrics?
Well, I don't think so. Pseudo means with a minus somewhere, right? That's what is.
Yeah, that invariance.
Yeah. Not that I understand.
Okay.
It is related to sub-Riemannian metric, as I tried to explain, and that's kind of obvious. And it's one very interesting aspect of it. I mean, essentially, in particular, you know, if you think about SUN, you have to ask yourself, what are all the possible sub-Riemannian geometry on SUN? And you know, any SUN is, as the Lie algebra is generated by just 2 vectors as Lie algebra. And so there are many, many different sub-Riemannian geometry, from those generated by 2 to the full ones that are Riemannian, and anything in between. And all of these different sub-Riemannian geometry will play a role, even if you are asking the question only for Riemannian geometry. And that's because you're asking this uniformly at all scales. And so that forces you to understand the sub-Riemannian geometries. Not
I was motivated to ask because of the Laurentian manifolds. That's more relevant in physics. Yeah, so the related question is that you said that these won't work for hyperbolic spaces, like light cones.
Yeah.
Where was the problem? Where is the problem actually?
Well, just because I'm asking this, in hyperbolic spaces, the volume of large ball is exponential.
Okay.
So, you know, I'm not saying there is nothing interesting related to what I'm saying here. I'm just saying that it's a different world where you have to ask slightly somewhat different questions.
So for other general compact Lie groups, have you did you give some counter examples in the early part of your talk? I don't remember.
No, in the
so far no counting examples, right?
no, there is no other. The only one are abelian, so the tori. And when we are done, we'll be able to do SU2 time any abelian tori. But that's about, I don't know, no, there is no other example, no.
Okay.
So I have a different question. We often get insight into heap kernels by using a Feynman-Katz representation. Is there any relation of using such representations to this work?
Well, because we are talking about the, in some sense, the Feynman-Katz formula is relating a complicated heat kernel to a simpler one, right? So in that sense, we are looking at the most basic one. And so maybe one could say, yeah, the question as asked here is too basic to be amenable using the Feynman-Katz formula. On the other hand, if you take a very all-encompassing point of view, here I have a formula which I didn't have time to explain, but absolutely key to our analysis, and I believe to any future solution of the conjecture, is the use of the wonderful Campbell-Baker-Hausdorff-Dynkin formula, and actually not just that, but this very long product. Here I wrote it as the series for computing the endpoint of a path. So now the reason I mentioned that now is that, okay, so the Feynman-Katz formula is using paths, right, to express it. And so here, key to this is the fact that a group can be built essentially using paths via expression from such as Campbell-Baker-Hausdorff-Dynkin formula. So in that sense, there is a sort of connection. And definitely the answer to the conjecture lies in a better understanding or finding a way to use these wonderful formula, which are really amazing, but also hard to understand and hard to decode and to speak to you.
Yeah, I have another question, Laurent. So is that known? I mean, the counting of eigenvalues, the estimate is uniform over all the conformal metrics, right?
Okay, so that's different question. Here I'm asking about two-sided bound on things, and to get that, it seems to me really that this volume doubling conjecture is essential, or is the basis for it. Now, of course, there is a huge amount of work on questions that relate to what I explained, all my 4 questions. So I started with these 4 questions. People have worked on this in many different contexts. So there are a lot of results, and I'm not mentioning it. And some of them will apply to compact Lie groups. They will not give the full picture, but they will give partial result, maybe one-sided and things like that. And in particular, in the reference here, I mention a wonderful piece of work here. This is a very nice work, recent work by Judge and Lyons, and they get upper bound for the spectral function on homogeneous space via volume growth, and it's very refined, very nice. It's very closely related to this talk in the sense that they prove consequences, one-sided consequences of that I mentioned here. They don't prove they don't talk or prove the conjecture at all, but they are getting directly to the spectral function, and they get very good result on one side.
Okay.
And that's a very nice work.
Thanks.
So are there other questions? Well, if there are no more questions, I'd like to thank Laurent again for a very nice talk, and look forward to seeing you in 2 weeks when we resume with a talk by Jinsum Wu, giving new inequalities from quantum Fourier analysis on quantum groups. So see you then. Thank you very much, Laurent. Bye-bye.
Thank you very much to everyone, and
Thank you. Bye, Laurent.
nice day.